This is Math 251, Section 14.1. We're going to begin talking about a new type of function for the last time this semester. These are called vector fields. And I want to take you one more time through the whole list of the function types that we've dealt with. Our original function, y is equal to f of x, had one independent variable, typically x, and one dependent variable, typically y. At the beginning of this term, we looked at vector-valued functions of one variable. T was our input variable, and our output might be a two-dimensional, so two outputs like x and y, or it might be three-dimensional, three outputs like x, y, and z. But again, typically one input, like t, and multiple outputs, x, y, perhaps z. In the last two chapters that we've been working with real-valued functions of several variables. Things like z is a function of x and y, or w is a function of x, y, and z. Here we had multiple inputs, like x and y, for example, but just one output. The inputs x and y led to the single output z, or the inputs x, y, and z led to the single output w. The only situation that we have not yet dealt with is what if there are multiple inputs and multiple outputs. So that's how we're going to finish out the semester. Multiple inputs and multiple outputs. This is the two-dimensional version of that. You can see that what's going on here is we've input the variables x and y, and our output is two new variables, f and g. This last function is what we call a vector field. Notice a vector input and a vector output. We can also write this for three variables, so just for practice, let's do that. If I had three inputs, f of x, y, and z, I might then have a three-dimensional output as well. I'm going to write it in vector form. Little f of x, y, and z, I, or in the first coordinate in this case, g of x, y, and z in the second coordinate, and h of x, y, and z in the third coordinate. So again, it's really a vector input, x, y, and z, with a vector output, f, g, and h. Multiple inputs, multiple outputs. All right, well, typically when we've looked at these, one of the first questions we've asked ourselves is, what do the graphs look like? If I want to graph a vector field, what I'm going to ask you to do is to think of the input as a position, and think of the output as a vector, specifically a vector to be graphed with its initial point at that input position. These are actually a real pain in the neck to graph. It's going to take a very long time. And so we're going to graph one simple one, or at least partially graph one really simple one. But I will be saying that really the only reasonable way to graph these is going to be with technology. So let's look at one that we can at least start to graph, just so you can get a feel for these things. And then we'll turn to technology to help. So I'm going to start with a really simple vector field. The vector field f is equal to x comma y. Or I might say f of xy is equal to xy. This function does nothing more than essentially turn the point into a vector. So my input is considered the point, and I'll think of it as an initial point where I'm going to start. And then my output is a vector from that initial point. So let's see here. Let's put some axes in. And I'm going to start with some points along the x-axis, so the y will be 0. I'm going to do 1, 0, 2, 0, and 3, 0. Again, my function does nothing more than take these same exact points and return them as vectors. So what is this going to look like when I actually try to draw it? Well, at the point 1, 0, I'm going to draw a vector that goes over 1 and up 0. So that vector represents this first input-output pair. Next, at the point 2, 0, I'm going to draw a vector that goes over 2 and up 0. Like so. And finally, at the point 3, 0, I'll draw a vector that goes over 3 and up 0. Notice that these vectors overlap, and that's very common. All right, we're going to do a few more. This time, I'm going to do the same 3 x inputs, but let's do 1 as the y value every time. In each case, our function turns the point into a vector. We're going to draw it. So at the point 1, 1, we draw the vector over 1 and up 1. At the point 2, 1, we draw the vector that goes over 2 and up 1. And finally, at the point 3, 1, the vector that goes over 3 and up 1. All right, a couple more here, a couple more rows or sets. This time I'm going to again keep 1, 2, and 3 as my x's, but let's do 2 in all the y values. The outputs become the vectors. And again, the only reason is because I picked such a simple function this time. So at the point 1, 2, I draw the vector that goes over 1 and up 2. At the point 2, 2, the vector that goes over 2 and up 2. And at 3, 2, I go over 3 and up 2. All right, I'm going to finally draw the vectors that have 1, 2, and 3 as the x's, but 3 in the y's. And my function turns each of those into the xy vector. So at 1, 3, the vector goes over 1 and up 3. And at 2, 3, the vector goes over 2 and up 3. And at 3, 3, the vector goes over 3 and up 3, like so. All right, I've drawn a few examples of outputs in my first quadrant only. Hopefully you can imagine that the same thing would be repeated but flipped down here, reflected this way and reflected this way as well. And so what we're going to get is sort of vectors that all kind of burst out from the origin, coming in all directions. This is called a radial field. And the reason is literally almost like it follows the radius going out and away from the origin. If I pop over to Maple, what you're seeing here is actually my radial vector field. Let me see. I can't quite get it on there. In Maple, this is called a field plot. I'll show you the notation in just a moment. But you're going to have to do a with plots and a with vector calculus. And then the word field plot followed by this. There's my vector, xy. And this just sets the window for x and y. And you can see this is what we were trying to draw, only they filled in the other 3 quadrants that I didn't get to. So again, in Maple, let's see here, let me just give this to you. You will have to do with plots and also with vector calculus. And then the command is field plot. You're going to put your vector in. So in this case, I just put in the vector x comma y. And then you can do x equals, I did -5 to 5, but again, whatever window you want. And y equals, again, I chose -5 to 5. That gives you the general method for finding or showing a field plot or a vector field in Maple. All right, let's talk a little bit more about this radial vector field that we just saw. Here are a couple of slight variations that make this perhaps a little bit more useful, to do models for. If I've got the variation xy divided by the magnitude of xy, notice that every single vector here is going to be a unit vector. So instead of my vectors starting out short near the origin and getting longer and longer as they move away, all of these vectors would have a length 1. They would all be unit vectors in this case. In this one, we're dividing by the cube of the magnitude. So the further away we get from the origin, the bigger the x and the y get, the smaller that fraction gets. The denominator will get real big, the fraction will get smaller. So all vectors get shorter. Further from the origin. This one is a particularly useful vector field. It can be used a couple of different ways. One way might be to consider this as a magnetic field, whereby you've got some positive charge here at the center, and this is showing the repelling charge, right, as our negative charge and positive charge, or with another positive charge, that they would repel one another. Now, when that happens, of course, the largest repelling charge is the one that's closest to our initial charge, and they get smaller and smaller as they go out. So this would make sense. The strength of the magnetic field is going to get less as we move from the origin. So we might say a magnetic field. One that's repelling. Another possibility would be if I use minus f, so I've got a negative in front of this, I would have potentially a model for a gravitational field. If you imagine all of these vectors coming in instead of out, now you've got your gravitational body, the Earth, or whatever it is here at the center, and we're pulling in towards it from all directions. That would be a model for a gravitational field. Again, it's best if the vectors out here are smaller. Gravity is weaker further away, and the vectors in here are larger. Gravity is stronger, closer to that origin or that Earth. So magnetic fields, gravitational fields, really well modeled by that vector field, or at least the opposite of it. All right, here are a couple of other vector fields I'd like us to just take a look at. F is equal to x squared j. If I go over to my maple graph, that one's right here. You'll notice I've got a 0 in for the I component and x squared in for the j component. All of my vectors are vertical here. None of them have any x component. X component is 0. And the y component, since it's x squared, is always positive. So notice that all of these vectors are pointing upward. The larger the x, the longer the vector, because x squared gets bigger and bigger. Even on the negative side, the further away I go from the origin, the larger x squared becomes. So my vectors get longer and longer as I move away from that origin. The other one we wanted to take a quick look at here was minus yi plus xj. Oops, and I'm going to have to do something down here to get you to be able to see that. There, that's better. So here I've got my minus yx, there's my vector, and I've got my same window, negative 5 to 5. And this is called a rotational vector field. You can see why. It looks like the vectors are all pointing around in circles, concentric circles going counterclockwise. So that's our rotational vector field. This is another important one that we use a lot. In order to investigate these more, you really would want to play around with them a bit in Maple. If you don't have Maple accessible, this section in your book also has got some examples of vector fields to start letting you get a little bit better feel for them as you're playing around with different vector fields.